Okay, all right, well, happy Wednesday, and it's week 9, where our time is ticking. Today we will take a look at Bootstrap. So on Monday we had randomization tests, and today we'll take a look at Bootstrap. And kind of the whole idea is that we want to do statistical inference, which means based on a sample of data, we want to draw conclusions about the population. And a key thing in order to draw conclusions about the population based on a sample is we need to understand the sampling distribution. The sampling distribution says if the population looks like this, when you take a random sample, your sample might look like this, okay? So basically, if the population has a mean of 100, when you take a random sample of, 30 people, the mean of your sample should be close to 100. Maybe it's a little higher, maybe it's a little bit lower. We would be shocked if the mean of your sample, if the population has a mean of 100 and standard deviation of 10 or something, and you take a random sample of 30 people, you shouldn't get a sample where the mean is 70, right? That just shouldn't happen. So the sampling distribution kind of tells us that. A lot of times we used the central limit theorem to figure out our sampling distribution. So central limit theorem says it's going to follow a normal distribution with this mean and the standard error. On Monday, we created our sampling distribution with the randomization test. We shuffled our values, okay? And we said if the null hypothesis were true, then who got which assignment, whether were in the seed yawn group or the regular yawn group, or whether you were in this group or that group, the treatment or control is just a random process, and so we use random assignment for that, okay? But anyway, key idea is we want to create a sampling distribution so that we can see what kind of samples we get, and therefore when we observe a sample, we can draw conclusions. So what did I put on this slide? I wrote sampling distribution of a statistic is the distribution of all the possible values of a particular sample statistic from all the possible random samples drawn from the population. By studying the sampling distribution, we get a sense of how much that statistic can vary from one sample to another. And then if you have data, you can compare your particular sample's value, sample statistic, to that of the sampling distribution and say, hey, my value is kind of like right in the middle of the sampling distribution. It's not that weird of a thing. Or maybe my value is really extreme. If this is the sampling distribution we're supposed to get under the null hypothesis, my value is like way out here, which indicates to me my sample isn't coming from this null distribution. It's coming from something else, okay? Or that null distribution, that null hypothesis is wrong. All right, central limit theorem says, yeah, if these certain conditions are met, and you were talking about the mean of a sample, the mean of the sample comes from a normal distribution, and that's nice, right? That holds true for a lot of cases. A lot of times we are dealing with the mean, so the central limit theorem is perfect for us, okay? Sampling distributions exist for any statistic, not just the mean, okay? It's just that when you're not dealing with the mean, you no longer have the central limit theorem behind you, okay? So if you're dealing with something like the standard deviation or the variance or something like that, it comes from a different sampling distribution. So what we can do is we can simulate sampling distributions. So if you don't remember like the mathematical rules and stuff like that, we can just kind of use our computer's ability to simulate random values, and approximate a sampling distribution, okay? All of these simulations require us to make assumptions about the population, but all of statistics requires us to make assumptions about the population. That's the whole premise of statistics, and I think I said this on Monday, is that you have a sample of data. There's a lot of stuff unknown about the population, but you want to make conclusions about the population based on your sample. And in order to do that, you have to make some assumptions. You have to either assume your sample is representative of the population, or you have to assume your population has these kinds of properties or certain kind of aspects hold true. And really, what you have to think about are like, what assumptions are reasonable? And if this is a reasonable assumption, then this is the process I should follow. On Monday, the assumption we were making was that of exchangeability. We were assuming that if this is my data and I got it via random assignment of treatment versus control, then any other possible permutation of those random assignments is reasonable to assume if the null hypothesis were true, and therefore I can kind of do this exchangeability stuff. Today we'll look at parametric bootstrap and non-parametric bootstrap, and you make different kinds of assumptions, okay? And so here we might make assumptions about the population's shape, the population's mean or standard deviation, or what kind of values appear in the population. But once you have a clear sense of what your assumptions are and what kind of assumptions you're comfortable making, then you can go about and simulate your sampling distribution. So let's look at an example, and this one will be, we'll do parametric bootstrap, and we'll make assumptions about our population. Okay, so parametric bootstrap will make parametric assumptions about the population. So I'll talk about what that is here. Okay, this whole concept about the bootstrap, it comes from kind of that idiom or the phrase, to pull yourself up by your bootstraps, which now has kind of this slightly, I don't know, I think there's a slightly negative connotation to this phrase about like, pulling yourself up by your bootstraps and stuff like that. It's kind of like, well, I'm not willing to help you out type of thing. But as far as this goes, it's kind of like, can we figure out our sampling distribution without really gathering additional data? If this is the only data I have, can I still do statistical inference without gathering much more stuff? Okay, I like to just throw this in here. Where does this phrase, pull yourself up by your bootstraps, even come from? And there's a variety of I think possible apocryphal origin stories. I think the one that's most fun for me that I like to just say is that there was a story about some folk hero who was going out and he was walking along, he got stuck in the swamp, and so his solution to getting out of the swamp is he bent over, grabbed his bootstraps, and he pulled himself out of the swamp, right? Again, a ridiculous thing, but it's just kind of a silly idea there. Okay. With the parametric bootstrap, though, what we're going to do is we're going to assume the population has some particular shape, some particular parametric distribution, and we probably have to specify the parameters of that distribution. So if you're saying it's the normal distribution, you have to specify your mean and standard deviation. But you might say I want to say the population comes from a binomial distribution with n and this p, or it comes from an exponential distribution with this lambda, or it comes from a gamma distribution with this what is it, scale and shape and scale parameters or something like that, and beta distribution with these numbers. You just say the population comes from this thing, you have to specify the parameters, and so you might feel a little comfortable, but in some cases you say, oh yeah, it makes sense to do this, okay? So once you specify that distribution, your computer has all of these functions that can generate random numbers from those distributions, right? You have R norm for the normal distribution, R binom for the binomial, R exp for random exponential, and so on and so forth. Pretty much every theoretic distribution that you learned in 100B, your mathematical stats class, there's a corresponding function on your computer that can generate values from that distribution, right? The Poisson distribution. And I don't know how many distributions did you learn? There's a whole bunch, and and you can generate random values from those things, and that's what we're going to use here. Okay, so we simulate drawing random samples from that assumed population. Whenever you draw a random sample, you're going to calculate whatever statistic it is. In the past, we've used the mean, but it doesn't have to be the mean. It could be, like the median, right? And what's the sampling distribution for median? Like that's way harder, okay? What's the sampling distribution for the max value of a sample? All of these things, like the mean, yes, that looks like the normal distribution because of the central limit theorem. But everything else, I think it's a little bit cloudy in our head, right? And then you can perform statistical inference. So we'll do this example, and this is I'm just curious. Did you guys take the SAT exam? Did anyone not take the SAT exam? I'm just curious. Okay, because I feel like the SAT, as far as college admissions goes, it's kind of like going through this transition thing where it used to be like required, then it became optional recommended, and then it just became optional, and now is it becoming not recommended? I don't know, okay? I think you guys were applying to college during the pandemic, and so I think that's when things started shifting, and I don't know what the future will look like. But anyway, the SAT verbal, technically it's the evidence-based reading and writing exam. It's supposed to be normally distributed. The mean is supposed to be 500, standard deviation of 100, right? So 3 standard deviations above the mean is 800, and that's your perfect score, okay? Scores have a maximum of 800, minimum of 200, and the SAT, as far as scores go, only go in increments of 10, so you can't get like a 522 or 521.8. It's either going to be 520 or 530 or 780, something to the nearest 10, okay? And technically, when you look at the actual distribution of scores, they are not normally distributed because the people who take the SAT is not the general population of senior high school students. It's people who are planning on going to college, which is a different group, okay? But let's say we do take a random sample of 15 random students, and then we ask, what's the sampling distribution of the variance of the samples, the sample variance, okay? So does anyone remember, pop quiz? What is the probability distribution that models the sample variance of a sample of random normal values? You guys remember? You learned this, right? 100B? Okay.
We're still in 100A.
Oh, you're in 100A. Okay, you haven't learned 100B yet. Okay, well, anyway. So, chi-squared. Chi-squared distribution is the answer. And maybe, but anyway, we'll go over this answer in a little bit. But anyway, even if you don't remember, you don't have to, okay? What we're going to do is we're going to simulate drawing a random sample from the assumed population, which has a mean of 500 and standard deviation of 100. But we also have to do a few things, like when you do R norm, you're going to get continuous values, okay? Well, floating point continuous, so not exactly continuous, but pretty close to that. But we have to round to the nearest 10. So we're going to use round, and we're going to say keep -1 places after the decimal. So normally round 0, we'll round it to the nearest whole number. Round 1, we'll keep it to the nearest 1 place after the decimal, 10th place. But you can also put in negative numbers, and -1 will round to the nearest 10. So like 540 and things like this, okay? If we're also going to use an if-else to kind of make sure the maximum value is 800 and the minimum value is 200. We're going to say if-else, if the sample is if the value is greater than 800, just replace it with 800. Otherwise, use the value in the sample. If the value in the sample is less than 200, replace it with 200. Otherwise, use the value in the sample. And so, so this is what I get. So here's my 15 values: 440, 520, 420, 660, so on and so forth. And I can say, hey, what is the variance of this sample of 15 random values? My variance is 10,120, which is kind of close to what my expected sample variance is. My expected sample variance would be 100 squared, 10,000, and I'm getting just a shade over that, okay? And I could say, all right, so that's one random sample of 15 values. What if I do this a bunch of times? So I'm going to just create a for loop. I'm going to say, hey, I want to keep track of 10,000 of these things, and every single iteration of my loop, generate 15 random values, round the values, max the 800, min the 200, calculate the variance of my sample, and keep track of it and sample underscore variance is I. And so I can say, okay, my mean variance is 10,045. Sometimes I get a sample where the variance is 29,838. Sometimes I get a sample where the variance is only 1,540. But most of the time it's around 10,000. My median is 9,600. This is what, these are the different kinds of values I get for my sample variance. And so this is a histogram of that, okay? And so we can see, yeah, most of the time we're right around 10,000, sometimes higher, sometimes lower, but this is the distribution of sample variances here, okay? Yeah, answer to the pop quiz is when you take a random sample of n values that are coming from a normal distribution, then the distribution of the sample variance is going to be chi-square distribution with n-1 degrees of freedom. You do have to put in the scaling factor, though, of n-1 over sigma squared. But yeah, if you plug in this thing, that's going to follow a chi-square distribution. And so if I put in that scaling factor, I can draw the theoretic chi-square distribution in this red line, and I can compare it to my histogram, and we see that there is pretty close alignment. Perfect alignment would be the red line goes through the center of each of these bars, and we see, yeah, this red line goes pretty much through the center of that bar, close to the center of that bar, close to the center of that bar. Not quite there, but you know, overall, pretty good alignment between the red line and my histogram there, okay? So yeah, it seems like, mathematically, it looks like things are following the theoretic distribution here. Okay. Let me go ahead and give you your first view quiz answer, which is the letter A. A as in apple, A. So if you didn't remember that the sampling distribution of the variance follows a chi-square distribution, or if you just hadn't learned it yet, that's okay. This is where parametric bootstrap comes in. We just say, hey, you know what, let's just simulate our sampling distribution by just drawing random values, right? So I was comfortable saying this about the distribution. I was comfortable saying SAT scores come from a normal distribution, and if that's the case, and I do this rounding or whatever, I've got SAT scores, and now I can say this is what my distribution should look like. Okay, so let's say we have this problem, and we say, hey, I have 15 students here. Is it reasonable to believe my 15 students are a random sample coming from this population, right? So let's say you have a sample of 15 SAT scores, and the variance of your sample is, say, 20,000. 20,000. And so now your question is it reasonable to believe that my sample is coming from a population, either is not a random sample from the population, or is coming from a population that's different from having a variance, standard deviation of 100, right? Because if the standard deviation of the population is 100, when I take a random sample, I should get a variance of around 10,000. And if you happen to have a sample where your variance is 20,000, is that going to indicate to you that your sample isn't drawn from this population, or isn't a random sample from this population, or something like that? We want to figure this out. So I can kind of go back and look at this thing, and I can say, well, first of all, can you get a random sample where the variance is 20,000? And the answer is yeah, it could happen, but look at it. It's kind of far out here. It's not a very common occurrence. So yes, when you draw 15 values by random, at random, can you get a sample where that variance is 20,000? And the answer is yes, but it's not very probable. But we can see, okay, exactly how many of these things are 20,000 or greater. And so I do sample variances greater than or equal to 20,000. This is going to be a logical true-false vector. And when I say mean, it's going to give me the proportion of values in that vector that are true. And it says, okay, the proportion that's true is basically 0.012, 1.2%. So out of 10,000, it did happen. It happened 120 times out of 10,000. So it's got a probability of 1.2%. So could a random sample of 15 values produce a sample where the mean is 20,000? It could. what's the probability of that happening? The probability of that happening is only 1.2%. So that's a pretty small number. And I think my conclusion is going to be, you know what? I don't think I was just the lucky 1.2%, right? I think something happened where either my sample isn't randomly drawn from this population, so maybe it's not a random sample, maybe it's coming from a different population, who knows, okay? That's going to be our conclusion here. So we're going to say, because my p-value is small, this is an estimated empirical p-value, but because it's small, we're going to come to the conclusion that that it's not coming from, that the null hypothesis isn't true in this case. Okay, does that kind of make sense, the process here? Okay. Let's try out another example. What if we were dealing with something like the highest score in a class? All right, so we'll keep working with SAT verbal scores, which are normally distributed with a mean of 500, standard deviation 100, but also a hard cap at 800. Okay, and let's pretend a classroom has 25 students, and these 25 students are a random sample. This is almost never the case for how school works. I don't know about you, but when I went to high school, I probably saw the same maybe 30 to 40 students in like all of my classes, just because I was kind of like put in the group of like, these students are expected to go to college, and so I don't know if that was the case at your high school, but usually they separate a lot of times. A lot of times they separate students into different things, and so having a truly random sample of 25 students, probably not realistic. But let's say we did have a truly random sample of 25 students. And I'm going to ask, what is the sampling distribution of the highest score in the class? Okay. Is there a theoretic distribution we could even use for that? Okay. And then here's another question. What is the probability that if you have a random sample of 25 students, what is the probability that the highest score in your class is 750 or higher, right? So 750 would be considered a good score, 2.5 standard deviations above the mean. And if you have 25 random students, what's the probability that the highest score is going to be 750 or higher? Okay, so there is a theoretic distribution you can use to describe something like the max value in a sample, and it's the Gumbel distribution. But I don't know if anyone's familiar enough to use it and do a hypothesis test using that. So it's kind of tricky, right? But you know what? This is what we often do here. Is like, the math is hard, okay? So let's just brute force attack this, okay? And we're going to just say, hey, you know what? I don't want to have to deal with figuring out the mathematical theory behind this. So let's just use our computer's random capabilities and kind of brute force attack this. And in this case, we'll use, the parametric bootstrap. So, our big assumption is we know what the population looks like, that it's mean 500, standard deviation 100. But we're going to generate random samples to do this. And so I'm going to say, hey, I've got a class of 25 random students. So I'm going to do R norm 25, mean 500, standard deviation 100. I turn them into SAT scores by rounding them to the nearest 10, force the max to be 800, force the min to be 200. And then I'm going to take my sample, I'm going to take the maximum value of my sample, and I'm going to keep track of that. Right? I do this 10,000 times. And so, yeah. 10,000 groups of 25 students, it's no surprise my max is going to be 800. The mean, so if you take a random sample of 25 students, what is the average highest score? Around 690, 695, okay? And so on and so forth. And we can create a plot here, right? And this is actually, we notice there's a hard cap at 800. And so actually, the theoretic distribution is not just the straight Gumbel distribution, but because the straight Gumbel distribution would assume the underlying population is normal, and if the underlying population was truly normal, it would be possible to get scores like 890 or 860 on the SAT. But that's because of the way that SAT is scored. The true max score is 800. Okay, and so we see there's kind of like this artificial cap here, And so it would actually be really hard to figure out the true theoretic distribution that's going to produce this this plot, right? You'd have to kind of take the underlying random value variable, apply this kind of transformation function, and then that just makes the math really hard because you now have this abrupt thing here. So in this case, I think the kind of this brute force parametric bootstrap method is actually easier to deal with. And so you can say, okay, well, how often is my highest score 750 or higher? Okay, and with a random sample of 25 students, there's around a 16% probability. So when you take a random sample of 25 students, around, about one sixth of classrooms of 25 would have a highest score of 750 or higher, or something like that, okay? Okay, what if we had 50 students rather than 25, okay? Now, what is the probability that our highest score is going to be 750 or higher? Just intuitively, should that number go up or down? Higher than 16 or what? Lower than 16%. We're going to have 50 students rather than 25. We're just going for the max score there. It should go up, right? If you have more students, then the highest score should go even have a greater chance of being really high. Okay, but yeah, how would you do this mathematically? Again, it's tough, but we'll just brute force it. Okay, and so all I have to do, the only change here is I just change the number from 25 to 50. Everything else about my code is exactly the same. And then now I say, okay, well, how often is the highest score greater than 750? I get my true false vector, what proportion is true, and now this number goes up to around 30%, 0.2965. Okay, so that's that. Okay, this is a tiny bit of a cynical take on school administrations, but let's say a high school has, say, 200 students in its senior graduating class, so I guess like a medium-sized high school or something, and then they look, students take the SAT, and let's say 10 of their students scored 700 or higher on the SAT verbal. And so the school administration's like, oh, look, we're doing a great job because look at these SAT scores. We got 10 students getting, these great scores and stuff, right? At least at the local high schools where I live, the students who are going to college, they have their pictures and they put them on little banners and stuff, and they're like, congratulations, and it's like so-and-so is going to UCLA and so-and-so is going to Stanford and stuff like that. And a lot of times schools celebrate great achievement, which they should, but now, this question is out of 200 students, if 10 of them score 700 or higher, is that something to celebrate, or is that just something that could happen just because of randomness, right? What do you guys think? Is this 10 out of 200 scoring 700 or higher? Is that I don't know, right? So you might be able to sit and figure this out. Again, parametric bootstrap, we just randomize it and just see what happens. How often does something like this happen? Okay, so what is the distribution of the 10th highest score? That's a weird thing to figure out, right? But anyway, it's easy with parametric bootstrap. You say, hey, I need 200 random scores, okay? Turn them into SAT scores. And now I'm going to sort them in order from highest to lowest, and we're going to take the 10th highest one, okay? And I'm going to store whatever number that is, we're going to store it as the 10th highest. And we want to know how often is the 10th highest score over 700, okay? And so I say, how often is the 10th highest score 700 or higher? And that happens 3.5% of the time. Okay? So yeah, you know what? If out of a graduating class of 200 students, if 10 of them scored 700 or higher, yeah, that's a pretty remarkable thing. I mean, it's not impossible, but it happens less than 5% of the time by random chance. Okay? So if this happens, yeah, the school could celebrate it. Now, whether that's because the school did a great job or whether they just happen to have this randomly remarkable class, who knows about that? But yeah, this is not a very common occurrence where the 10th highest score in a class of 200 is going to be 700 or higher. Okay, but I think this kind of question would have been a lot harder to answer if you didn't have the randomization tools of the computer. If you were just given this on an exam and you had to figure this out theoretically, I think it would be quite challenging. I don't think I would be able to do it myself, right? Just using theoretic tools. So, all of these things, you have to be comfortable making some kind of parametric assumptions about what the distribution looks like. But if you're comfortable with that, then you can use parametric bootstrap. And again, in our examples, we've been using the normal distribution for the SAT score things, but in other cases, you might be like dealing with, I don't know, some kind of casino game, right? In a casino game, those should be dictated by rules of probability, and you can use, a binomial distribution or perhaps a Poisson distribution or exponential distribution, and you say, because of the setup of this thing, it makes sense to use this particular random distribution to describe my thing, right? So you're talking about the Poisson distribution. You guys learned about that, right? And then so that's like how many random events happen within a certain period of time and stuff like that. So you can start asking questions about that, even if you don't fully understand how do you go about getting the 10th highest value in that thing. You can do it. Okay, let me go ahead and give you your second view quiz answer, which is the letter C. C as in cat. C as in cat. All right, let me now talk about non-parametric bootstrap, okay? So when somebody talks about bootstrap, they probably are thinking non-parametric bootstrap. Non-parametric bootstrap is traditionally what's just referred to when we just use the word bootstrap. So what we've been doing earlier was parametric bootstrap, but non-parametric bootstrap is probably what people think about when they think about just bootstrap. So the difference here is that in non-parametric bootstrap, we are not going to make any parametric assumptions about the population, which kind of makes sense because it's non-parametric. So we're not going to say the population has this particular distribution with this parameter or this and that, okay? Instead, we make different assumptions. And there is a jump in our assumptions that might make you feel a little bit uncomfortable, but they're also kind of reasonable things. So the first assumption is the sample you have is a random sample, okay? So you have to look at your data collection process, and if it's reasonable to say the sample of data I have is a random sample, then you can move on. And then so the next conclusion, or the next assumption is, if my sample is a random sample, then it is reasonable to assume that it is representative of the population, okay? I think that's a reasonable thing to go, right? So if you say, all right, this was my data collection process, and based on that, I feel comfortable saying it's a random sample. If my data is a random sample, then I feel comfortable saying it should be, okay, again, not guaranteed, but if it's a random sample, it should be a representative sample of my population, okay? The next jump may be a little bit harder. If it is reasonable to say my sample is representative of the population, then to simulate the entire population, what I can do is clone my current representative sample a whole bunch of times, and that can act as a stand-in for the entire population, okay? I don't know if that feels okay. It's kind of like the idea of, I don't know if you've ever used Photoshop, there's like this clone tool where you can kind of like take a patch of grass and then you like copy and paste it and clone it, and you can fill in an entire field with that patch of grass, okay? And if your patch of grass looks like a typical patch of grass and you fill in the entire field like that, then your field might look kind of like a regular old field, okay? Or maybe like sometimes in video games, you'll have kind of like these this crowd of NPCs, not non-player characters, where you just kind of have like, but if you look closely, what it is it's like the same kind of character model, but it's just like duplicated a whole bunch of times, and so it looks like an entire kind of crowd. But if you look really carefully, you're like, hey, wait a second, it's that same character, you know, showing up multiple times, okay? But the idea here is that if you have something that looks kind of representative of the population, if you said, hey, I need to have this huge population, what you can do is you can just take your sample, duplicate it a whole bunch of times, and now you have this big entity that looks kind of like the population, okay? But, you know, if there's something weird about that sample and you duplicate it, then you're going to have a whole bunch of like weird things in your population. So, you know, just kind of like if you take that clone patch of grass and you clone it, but in that patch of grass there's like a funny hole in the grass, and you duplicate it, then your field's going to look funny because you got a bunch of holes, you know, spread out all over the field. That's going to look kind of funny. And similarly, if in your random sample you happen to have this one outlier that's kind of weird, and you do this, you're going to end up having a population that has a whole bunch of these outliers in kind of this weird fashion, okay? But that's kind of the big assumption in non-parametric bootstrap. You're saying, well, if my sample is representative of the population, or should be representative of the population, then it's reasonable to take my sample, clone it a whole bunch of times, and have that stand in for the actual population, okay? So that's what we're going to do in non-parametric bootstrap, is we effectively just clone our sample a whole bunch of times and have that stand in for the population. Now, on a practical level, you don't actually have to copy and paste your sample a whole bunch of times. What you can do is you can just sample with replacement. So sampling with replacement is mathematically equivalent to creating infinitely many duplicates of your sample as the population, okay? So actually, rather than actually duplicating the data, we draw samples with replacement, and that's the equivalent of creating infinitely many copies of my sample to create my population. And so now that I have my, quote, stand-in or fake population, then I can generate sampling distribution here, okay? When do you use which? So on Monday we looked at the randomization test. Today we're looking at Bootstrap. Basically, the key here is if the data you have came from random sampling, you can use non-parametric Bootstrap, okay? If the data you have came from random sampling and you're willing to make parametric assumptions about the population, you can do parametric Bootstrap, okay? On the other hand, if your data came from an experiment with random assignment, then do a randomization test, right? So those are kind of your key differences. So usually you're in one situation. Either you have a random sample of data, and it's reasonable to assume it's representative of the population, and you use non-parametric Bootstrap. Or you've done an experiment where you don't have a random sample, but in your experiment you use random assignment. If you have used random assignment, then you can assume exchangeability and do a randomization test. So those are the kind of the differences there, okay? In all of these cases, we're simulating our sampling distribution. Okay, so this example comes from a textbook that we're going to use. It's an older textbook. It's dated, okay? But it's free for use. So this is the trade-off, right? So in homework 6, I think I have a link to this textbook, and you don't have to pay extra to use it. I shouldn't say it's free, because you are paying for it via your tuition, which funds the library, which then gives you access to this electronic catalog, okay? But it doesn't cost extra. So and we're only using a few chapters. I didn't want to like make you guys go to the bookstore and buy anything. I tried to keep all of our textbooks like no additional cost to you. The trade-off is you're getting a slightly dated textbook, because the publisher is like, the newest stuff, they want you to pay for it. So we get a slightly dated textbook. It still fulfills kind of the what we need it to do, okay? But also the examples that we get are also going to be a little bit dated. But so this is going to be this is the example coming from the textbook. and it's the example we can use for Bootstrap. Okay, so what they're looking at is they're looking at from the U.S. Census Bureau. They were looking at information about immigrant populations. Okay, and specifically they're looking at Latin American immigrants and Mexican immigrants. Okay. And it says, although the average immigrant is approximately 40 years old, large numbers are children who enroll in U.S. schools, and then their subsequent educational achievement affects not only their own prospects, but also those of their family, communities, and the nation as a whole. These researchers, Stamps and Bowen, studied the educational achievement of Latino immigrants by examining a random sample from the 2000 census data, okay, and it's in this CSV file. And so this is coming from the 2000 census, and they're looking at the educational achievement of these adults, which means these adults arrived even earlier, probably back either in the 80s, possibly the 90s, or earlier in the 70s or something like that. So this is like old data here, okay? And one question that these researchers had was, is there a link between where the immigrants originated and their subsequent educational achievement? Specifically, is there a difference in the educational achievement of immigrants from Mexico and that of immigrants from other Latin American countries? Okay, so that's kind of the question that they're going for. Again, old data coming from the 2000 census, so I don't know if any of these things would still hold true here. This is kind of the descriptions of the variables that they've included in this data set. And one of the variables, this is kind of the response variable that we're interested in, is this measure of educational achievement. And it's supposed to be a number from 1 to 100, where 100 indicates higher values of higher levels of educational achievement, lower values indicate lower levels of educational achievement. I'm not a fan of this variable, specifically because I don't know what any of these numbers mean. Like, if somebody graduates from high school and that is their highest level of educational achievement, I have no idea what number that is on this thing. Is that a 50? Is that a 60? Is that a 40? I don't know, okay? If somebody goes to college and graduates with a 4-year degree, what number is that? If somebody goes to medical school and becomes a doctor, what number is that? I don't know, and it's not just detailed in here. So, if there was like a final project and I said pick your own data set, and a group picked this data set, I would grill them on this variable, and I'd probably say you're not allowed to use this because you can't explain to me what these numbers are. But whatever, it's coming from our textbook, and so we'll just have to assume that these numbers are reasonable. But again, I have no idea how they did this, and when we look at the actual numbers, I have even more questions. Okay, other variables are the year in which they immigrated to the U.S., the age at the time of immigration, is the individual fluent in English, and then the variable that we're kind of focusing on is, did this immigrant come from Mexico or a different Latin American country? So this is all immigrants coming from Latin American countries. So is it Mexico or some other Latin American nation? That's kind of the thing we're going to see. Is there a link between that and educational achievement? So you see this, and really this is kind of the question. And so this column, did they come from Mexico or somewhere else, is here, and then their educational achievement. And so you can see, the data are people immigrating to the U.S. in the 70s, 60s, 50s, 80s, something like that, right? But again, this educational achievement column, I really have no idea. Here you have a 63.1 and a 63.7. And I really want to know, what is the difference in educational achievement between 63.1 and 63.7? Because it's on a scale of 1 to 100. So if you say, what's the difference between a 63 and a 64? I have no idea. And especially if you're going to even give me more finer tuned things like a 63.1 and a 63.7, what is that? Is that like 3 extra weeks of school? I don't know, because generally, how much schooling does someone have? It's usually between high school is 12 years of formal education, a bachelor's degree is 16 years of formal education, and a PhD might be what, 24 years of formal education, or a doctorate degree, I don't know, 20 something, 22 years of formal education, and we're turning this into a 100-point scale, and then we're going into granularity to the 10th. So what is 63.1 versus 63.7? I have no idea how they're measuring this. So I really don't like this variable to begin with, but we're gonna just, that's beside the point. This is just to show us kind of Bootstrap here. Okay, but anyway, we'll just gather some summary stats. And so we had 150 people in our data set. 116 people came from Mexico. 34 people came from other Latin American countries. If we take a look at the 116 people who came from Mexico and we take the average of their numbers, we get a 58.6. Again, I have no idea what that is. If we take the average, the mean of these 34 people, we get a 64.5. I have no idea what that is, and so the question is, okay, we're getting two different means, 64.5 versus 58.6, a difference of around 6 points, 5.9 points, and the question is that difference statistically significant? Okay, so we'll do that. Okay, here's a box plot. This is kind of what it looks like, and what does this even mean? I don't know. Okay, 64.5 versus 58.6. But the question is, could we get that just from kind of random sampling? Here's a density plot rather than a box plot. Okay, and so we have these kind of different peaks, and I imagine these peaks correspond to things like graduating high school, graduating college, finishing something else. I don't know. I really don't know. Okay. We could just take a traditional classical approach and do a t-test. Okay, t-test, you would have two samples. You're comparing the means of your two samples, and you do that. Your null hypothesis is that the difference between means is 0, and the difference between means is something other than 0. And here we get a p-value of 0.04597, so just under 5%. So if we're using a significance level of 5%, we'd say, yeah, our p-value is just under 5%, so I guess we'd reject the null hypothesis, and we'd have, I guess we have some evidence that that the means aren't the same. But again, we're barely on that kind of cusp of is it significant or not. You'd probably want to do further analysis. Okay, but let's try non-parametric bootstrap. Okay, non-parametric bootstrap, we're going to assume our sample is representative of the population. Okay, and so we say, how should I simulate my data if the null hypothesis were true? If the null hypothesis were true, we're basically saying that these values here, okay, in this achievement column have nothing to do with this column of whether the immigrant came from Mexico or a different country. Okay, if the null hypothesis were true, the numbers that show up in this column, they're just coming from this one population, the population of educational achievement values for all of these immigrants. Okay, they're all just coming from the same population, and so I could just draw another random value for this person, another random value for this person, another random value for this person, and that's what I'm going to do. I'm just going to draw values at random. Okay, the alternative is basically saying these populations are different, and if the immigrant came from Mexico, that population of values looks like this, and if the immigrant came from a different Latin American country, that population looks like this, and you should draw your values from different things. That's what the alternative says. But the null hypothesis says there's no difference. All of the values are just coming from one population. Okay, so we want to be able to simulate that. So how are we going to do that? The way we're going to do that is we're going to just draw two random samples from the exact same population. What is that same population that we're drawing from? It's going to be our 150 values that I'm going to clone 1 billion times to create my population. Or really, I'm going to just draw from the 150 values with replacement. Okay, So I'm going to draw one sample of size 116 with replacement from the 150 scores. I'm going to draw the other sample of size 34 from the same same population, 150 scores with replacement. We'll calculate the group mean for each of these things, calculate the difference, and repeat this a whole bunch of times. And so this is what the non-parametric bootstrap looks like. I'm just drawing from the same exact population, which is just my 150 scores with replacement, 150 scores with replacement. But because my samples are different sizes, I draw one with a size 116, the other with a size 34. Put that in group A, put that in group B, calculate the mean, measure the differences, and record them. Okay, let me give you your last view quiz answer, which is the letter E. E as in elephant, E. E is your last view quiz answer. Okay, and so we do that and we say, okay, how often did we get a difference of whatever, 5.9 or more? And we get something around 4.6%. So this aligns very closely with what we got from the t-distribution or t-test. So that's a good sign, I guess. So we get something very similar to that, and that's that. We've run out of time. I've got a few more slides, which says, what if you wanted to take a parametric approach to this? And hopefully you can read through the remaining slides on your own to kind of make sense of it. But we'll wrap things up here. So have a great rest of your day, and we'll see you on Friday.